Hi everyone. Today we're going to take a look at the concept of specific heat. Specific heat is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. Alright, I want you to think about something for a second. Take a look at this picture here, and let's say you had to choose. You had to choose one or the other. Option 1, you would hold on to these metal tongs which appear to be holding a red hot horseshoe. Option 2, you would put your hand inside this rectangle of water and allow someone to drop this horseshoe into the water. Which option do you choose? Hopefully you chose the water option. Reason why? Well, if you think about metals, one of the properties that metals have is their ability to transfer heat. They allow heat to flow through them very, very easily. Whereas one of the properties of water is that it resists heat flowing through it quite a bit. So in the case of specific heat, if it's the heat required to raise 1 gram of it 1 degree Celsius, the heat would transfer through the metal much easier than it would transfer through the water. In fact, your hand would be very safe as long as the hot horseshoe did not hit your hand, because basically it would the metal would come to equilibrium with the temperature of this little sample of water very, very quickly. However, as you know, if you hold on to metal tongs, that heat just rises up the metal and eventually would start burning your hand. Okay, so that is the idea of specific heat. It's the ability for something's temperature to go up. So I want you to take a look at this table. This table has various substances and what their specific heat capacities are. So I want you to take a look at this one here. That was the one we just looked and talked about, H2O liquid. It has the highest specific heat of most common substances here on planet Earth. If you look at everything else goes down quite a bit, from ice to aluminum, to iron, to mercury, to carbon. Each value seems to be going down because these materials here are easier to heat. So heat is going to flow through these with much greater speed than a water sample. Think about if you had to cook some food. Let's say you're making mac and cheese on the stovetop after school one day, and you put your pot on the burner and you turn on the heat full blast. You know the metal gets hot very, very quickly. But you also know if you put in a certain volume of water, the water seems to take forever to heat. Okay, 5, 6, 7 minutes you'll wait while that water slowly raises in temperature. If you know anything about pools, you also know they're extremely difficult to heat to get from ultra freezing to tolerable. It takes quite a bit of heat and or sunlight in order to do that, usually a combination of both. So let's go ahead and summarize some ideas about specific heat. Here's the first one. The higher the value, the more heat required to raise the temp. So in the case of water, this one here at 4.18 is the highest our chart goes. So it requires quite a bit of heat to raise the temp. On the other hand, if we have something like a metal, we have less heat required to raise the temperature of those substances. So water's value then is very high and metal's values are very low. Now, how we're going to use this idea is in the formula for specific heat, which you can see down here. And we have 4 different variables that play a part in the specific heat formula. We have Q, which represents heat. We have C, which represents the numerical value of the specific heat, which you just saw in a table. M is mass. Delta, as you know, is change in, and T is temperature. So heat, specific heat, mass, and change in temp are the 4 variables. Now, of course, we're going to need 3 out of 4 in order to solve for a missing variable in a specific heat question. So hopefully the data will be there to provide us at least 3 out of the 4. One additional thing about change in temp. Change in temp is also thought of as final temperature minus initial temperature. So here you can see that T sub F, that's final temperature. T sub I is initial temperature. The difference between those two temperatures is your change in temperature, or delta T. Okay, let's move on and take a look at some example problems. In this first question here, we are to determine the specific heat of a material if a 35-gram sample absorbs 96 joules as it was heated from 293 to 313K. So there's a lot of information here, and the best thing we can do is organize it by way of a table of known values. So I'm going to go ahead and put all of those variables that we just saw in the formula down here, and we're just going to fill in the table as we go. As we come to new data, we'll pop it into each one of these letters that best represents it. And let's think overall, even before we do that, of what's happening here. 35 grams of a sample of something is absorbing energy as it's heated from 293 to 313. So the overall picture is something is getting heated up because it's absorbing energy. Okay, now a couple of keys here. When you see joules, most of the time it's referring to heat. So we have 96 joules, and our mass is given as 35 grams. Our temperature was given from as a range. It started at 293, so that would be initial temp, and it finished at 313, and that would be final temp. So again, T sub F minus T sub I gives you your delta T, your change in temperature, and of course 313 minus 293 is 20K. Alright, so we can go down here to our table of known values, pop in 20K, and since it says determine the specific heat, that is going to be our unknown variable. So I'm going to go ahead and I'm going to put a question mark in there for letter C. Alright, moving on. We know the formula is Q equals CM delta T. But what we're going to have to do is rearrange that formula to best help us. We want to isolate C. So that means M and delta T have to be removed from the right side of the equal sign, which means the M is going down here, and the delta T is also going to go over to the other side now as a denominator. So we have Q now divided by M times delta T gives us C, and we're ready to go. So next thing we're going to do is just a little plug and chug, where we plug in the values from our table of known chart, and we chug them through the formula and through our calculator, of course. Alright, so here we go. We have 96 joules divided by M, which is 35 grams, and our delta T, our change in temp, is 20K. Now, one thing you may want to do, make that a better 9 for you, is put the bottom denominator in parentheses. It's going to allow your calculator to understand what you're trying to make it do a little bit better. Okay, so we have a simple math problem here. With a calculator, it's no problem. If you want to pause the video now to go ahead and calculate it, I'll do the same, and I'll see you in a second. Alrighty, so my calculator screen has quite a few digits on it. It has 0.13714 and a whole bunch of other stuff. Now, can we just leave that as an answer? No, we got to tidy it up. First of all, let's go ahead and check out our sig figs to make sure that we're reporting our answer to the correct number. Here we have 2, here we have 2, and we have 3 over there. So we're going to report it to 2 digits. And with specific heat, it's going to be 0.14, and I changed it to 0.14 because of that 7. The 7 rounds up that 3. And what about the unit on this thing? Well, we got to take a look and see what is still there. So I have joules, I have grams, and I have Kelvin. So nothing really cancels out. So what I'm going to do is I'm going to put joules over G times Kelvin, which is totally fine. Some of the times when you see it on a chart, it will be grams times Celsius. But if you remember, Celsius and Kelvin, as Celsius goes up 1 degree, Kelvin goes up 1 degree. As Celsius goes down 4 degrees, Kelvin goes down 4 degrees. So they have a 1-to-1 ratio. However, they are shifted in the scale, the Kelvin being 273 higher. So it's okay that we go ahead and put Kelvin there as well. So this would wind up as our final answer here. And if you were doing scientific notation, of course, it'd be 1.4 times 10 to the negative 1 joules over G times K. And that is how we do a specific heat problem when we solve for C, the variable for specific heat. Okay, let's try a little bit tougher one next. And the next one I really like, because it makes you do a couple of extra steps here that we didn't have to do last time. So what I'm going to do is I'm going to go ahead and put a table of known values one more time. Again, staying organized is very important in chemistry. As soon as you become disorganized and you start forgetting about the small things, bad things happen in calculations, like with units, and coming up with the wrong unit or the wrong exponent, or all kinds of things can happen. So staying organized is your best bet. Okay, so in this one, if 980 kilojoules of energy are added to 6.2 liters of water at 291 K, what will the final temperature of the water be? All right, so it's telling us right now, this is the initial temp right there, 291 K. We're also given Q, we're given a volume, and the volume, we're going to have to get smart here, and we're going to have to be able to change that volume to mass, but it's not very difficult. All right, so let's go ahead, we'll pop in 980 kilojoules for Q. Now, one thing before we leave this energy that went into it is that our unit is in joules. And so what that means is we're going to have to convert this to regular old joules. So what we'll have down here is the conversion of kJ to J, kilojoules to joules. And if you remember what kilos are, the prefix kilo, it means 1,000. So what we'll have here is 980 times 1,000, and that will give us 980,000 joules. Okay, remember with converting units, you can cross off things that you see twice when one's above and one's below a division line. All right, that brings us to our volume. How in the heck are we going to get our mass from that? Well, if you think about it, and you remember the conversion of milliliters of water to grams of water, you can think this through. So we said that 1 milliliter of water is equal to 1 gram of water. It's a very easy conversion. And I know that in a liter, I have 1,000 milliliters. And here, I have 6 liters. So I have 6,200 milliliters, which I'm going to convert to 6,200 grams. So for mass then, and if you want to see the unit conversion, we can definitely do that. 6.2 liters. I know that 1 liter has 1,000 mLs. And I know that 1 ml of water of H2O equals 1 gram of H2O. So that means I have 6.2 times 1,000 divided by 1, which is just 6,200 grams. All right. Now, the last thing that we got to worry about here is our delta T. Now, we are going to solve for delta T, but we're not interested in delta T as a final answer. We're going to take our answer one side step from that, and we're going to use our brain at the very end to figure out what our final answer should be. Okay, now the last thing that I'm noticing here is I'm missing a value for C. And because I'm missing a value for C, I better look closer at what I'm given. And I find the substance identity as water. Now, if you bring back up the previous slide or any table out of your book, you can see that the specific heat of water value is very easy to find. It's usually the topmost value, 4.184 joules over G times either C or K. All right, so now I got 3 out of the 4. Okay, so what I'm going to do then is I'm going to set it up so I can find delta T first. And to do that, just like before, I'm going to have to isolate for that value. C is going and being divided out from the right-hand side, now being put on the left-hand side. So what we wind up with then as a final formula here is Q over C times M equals delta T. All right, now at this point, we're going to start plugging and chugging. So above our division line, we'll have our 980, whoops, there's a better 980,000 joules. Underneath the division line, we have C as 4.184 joules over G times K. And then lastly, I have my M, which was 6,200 grams. Okay, and all of that equaled delta T. All right, so let's go ahead and you can pause it to do the calculation. I will do the same. One last thing, remember to put this in parentheses here so your calculator understands you better. And I'll see you in a second. Okay, so my calculator screen wound up with a delta T value of 37.77 and a whole bunch of other stuff with it that I probably won't need because of significant digits. Okay, so what do we do with that? Well, let's go back to the question. It says if a certain amount of energy is added to 6.2 liters of water at 291 K, what will the final temperature be? So we know the initial temperature. Remember a couple slides ago I said that delta T equaled T sub F minus T sub I. So what we could do then is we can pop in those values and calculate and figure out what T sub F would be. Okay, so T sub I, the initial temp was 291 K, and our delta T was 37.77. So T sub F minus that. And to get T sub F all alone, what's going to happen is we got to add 291K to both sides. And what we get then is 37.77 plus 291. I'm kind of running out of room here. I'll put an equals over here. 37.77 plus 291 gives us 328.77, and again a whole bunch of other digits, and that would be Kelvin. Alright, so that would be then our final temperature. Okay, our T sub F has now been calculated for. 328.77 is our final value. Alright, so we've been through a couple examples of how specific heat works. We've talked about what it was. Again, it's the amount of heat required to raise 1 gram of the substance 1 degree Celsius. Water and liquids are very high, and metals are very low because of their great ability to conduct heat. So I hope this helped you. Keep reading that book, keep doing examples, and you'll get better at this, and I'll see you next time.